in this class or project, actually we choose three different kind of models. One undoped cis polytetraline, and then one is p-dop type, and another one is co-dop, and there we include sodium, potassium, and fluorine, uh, fluoride. So there is three types of model there, and from that model actually we using DFT we want to plot absorption and density of state graph, and we want to see that which material show more conductivity than others.
Okay, and let's discuss the figure. Maybe there will be questions about the figure.
Okay.
So and everyone is welcome to just intervene and either speak or type question. So I see the first question from Mead Erickson. He's telling, I'm quoting his words, I don't know the definitions of P-type, N-type, or PN-type doping. Can you explain it to me?
Okay, so I need to go up because I didn't memorize those things. So there is two type dopamines, and one is P type and another one is N type. So mm, when we add any materials in the if I'm wrong, please, professor, please explain those things.
And maybe you keep showing the image, so it is easier to think about it. Image of the model. Yeah.
Yes, sir.
Uh-huh.
Okay.
Yep.
So if suppose in a material we want to show the conductivity, so what we did, we create a hole and add some material or what, like sodium, potassium, in this kind of atoms inside there, and we want to see that how it reacts when we are doing the calculation, like injecting charge or something like that.
Okay, Kia, to complete the answer to me, what the letter P means and what the letter N means in this P type and N type.
Then I need to show him
No,
here.
no. Just answer. You don't need to show this chemical structure. It's universal. So what is P and what is N? Not in this exact case, but generally. What the letter P abbreviates for and what is letter N abbreviates for. And Mid, you can guess yourself as well.
For good. Professor, could you please
What?
answer his question?
So Mid, would you like to type or speak? What is P and what is N? Just Kia, please do not move. We just discuss it verbally. Okay.
Because I can't see anything. I'm sharing my screen, so I'm not able to see anything.
So Mead is suggesting that N nitrogen, P phosphorus. Do we agree with it? Maybe let's ask Amir. Amir, would you please share your guess?
I hope it is correct. So N-type doping is when the system is negatively charged. So if I'm not wrong, N stands for negative.
Mm-hmm.
So it means that addition of or injection of the electrons, for instance, adding 2 or 4 extra electrons to system, makes it negatively charged. So it could be either by injection of the charge carrier or electron, or add some materials with extra electrons in their valence shell. In the other hand, for the p-type doping, it means that positively charged. It means that we get rid of some electrons from the system. Maybe I'm not such that familiar with the p-type material. Maybe some acceptor units or some materials with some holes in their electronic structure. They will cause p-type doping. Actually, in the simple way, electron charge is negative. As soon as you add more electron to the system, it would be negatively charged. If you get rid of or withdraw some electrons from the system, it could be positively charged or p-type doping.
Great. Yeah. Thank you, Amir. So, are there more questions to this figure one?
So now, Kia, can you tell me what is p-n type doping? This is the first time that I faced this term. You have both?
Yes, there we have both. In the co-dopt means this one there.
So it means that you add one material, one acceptor and one donor material to the system. Something like that, technically?
Yes.
Interesting. So what's the purpose of this kind of doping?
What I understand that we actually want to see that normally we used one type of dopant, like doping, not p-type or n-type, but what professor want to show us that if we add two things together, and does it will show more conductivity or not?
This is only a partial answer. I know that there are some attendees of this meeting who can answer, but if there are volunteers, please do. If not, I'll briefly cover. Amir, so the photovoltaic technology is based on interface between p-doped and n-doped. So if there are simultaneously p and n-doped, then one can model photovoltaic effects by modeling charge transfer between p and n-doped regions. Would you buy this?
So it will improve when we have both. It will improve the charge mobility, total charge mobility of the system.
Hopefully, those are potential motivation, and in what here is offering, it is more basic science investigation of properties. But yes, hopefully it may increase mobility, and it could help to photovoltaics. Okay. Are there more questions to this figure one?
I have a general question about the system size. It seems a little large system. So how many ions do you have here in your periodic model? How many atoms?
Atoms.
Yeah.
So
you do not need to give exact numbers, just roughly. Is it like 100,000, 10,000, one atom? Just briefly to get an order of magnitude.
Should be around more than 400,
like,
right?
3 models and different atoms. Like I think this one for the undoped 900 something. I forgot the exact answer. I forgot. This one 1,000 plus. This one also 1,000 plus.
Okay. And can you explain what is this model? What is composed of?
What is composed of, or?
Yeah. Just explain what is your model. What is chemically? Is it like a single molecule, many molecules? Is it like solid or amorphous? Just explain what you're modeling.
Sorry, Professor. Then no, I don't get it. What?
Which material you are modeling?
Polytectoline.
Polyacetylene. Is it like a single molecule of polyacetylene, or is it several?
There are several chain here.
Okay.
So so in every chain, it's not chain, so called oligomer. So there are several monomers inside.
So you have a multiple oligomers.
Yes.
In one simulation cell.
Yes.
So what's the length of one oligomer, and how many oligomers do you have?
Length.
Just approximately. You can either count on the image or tell approximately. Do not be exact.
There are around 6 oligomers, and in every oligomer maybe 14 or 12 monomers inside.
Okay. Yep. Good.
Yeah.
What is the shape of your simulation cell? Is it like a cube, square, pizza box?
It's like a one kind of rectangle, not a cube.
Mm-hmm.
Rectangle. Sure.
Okay. If there are no more questions, no. So please go forward. Whatever you want to show.
Okay. So after that, because just I'm not expert in those kind of things, so I'm trying to plot density of state graph for neutral, anionic and cationic state. So I did that one for all model, and after that I'm
wait. There could be questions
okay
to the figure. So let's check if there are questions to this figure.
I have a question.
Yes, please.
So I'm not, as Kia, I'm not such a familiar with this kind of plots for the LUMO. Is there any system that, or any orbiter that is partially occupied in this system?
Yes, because like when I'm doing this work, I read in the paper and from the Google that because these materials are conductive materials, so there is no band gap, like HOMO LUMO actually overlap with each other.
So they
that's
should
why
be
we are not
conductive.
Yes, yes, that's why. And they are conductive material. All are conductive material, and that's why they show overlapping. So if we want to see the band gap, what's the band gap? We need to go to the data. Then after that, otherwise it's difficult to understand from the figure, I guess. For me, it's difficult because it's already overlapped. I don't.
Okay, can you please explain your panel A? Which configuration, so which model, which configuration, is there a band gap, and how big it is?
So this one is undoped, means only 6 polytectoline. There is no doping added, and it's a neutral state. And
no, keep explaining panel A. What it is? What is the size of the gap? Like indicate where is HOMO, where is LUMO. What is the gap between them? Is it you expect it to be conductor or insulator? Just tell a little bit more.
Okay, so the value of the band gap it's written in the paper, it's around actually is 0.3 is something. So and from this figure means A, only A, the undot neutral in a neutral state, we're able to see that in a occupied orbital and the unoccupied orbital actually in like it's attached together, it's already overlap with each other.
No, if you take smaller width parameters, they will be quite separated. They're about 0.4 electron volts away from each other, which is noticeable band gap.
Means if I'm like doing 0.2 to 0.8, then it will show the band gap. You want to say
So
that?
you have peaks. Can you indicate the filled and unfilled peak with your marker? So the filled is at 0.4 electron volt and unfilled is at 0.8, right?
Yes.
So the offset between these peaks is 0.4 electron volt, almost half electron volt. So it is noticeable band gap.
Okay.
Okay. So do you expect it to be conductor or not quite?
It's like it it's show conductivity, but it's not um, much enough. Like
Okay, so
not
it is
good enough. Sorry, not good enough.
not very high semiconductor. Now let's look into the chat line. As we speak, it has already accumulated several questions.
I don't know.
So Mir is asking, this question can be for anybody. My understanding is that polymers are generally semiconductors. Why there is no gap? I think Mir is not. You can argue with him, at least about panel A.
Okay, there is a band gap. Sorry.
Okay, yes.
There is a band gap, but here, like when we did calculation for the anionic state, means removing electron from this, then
Okay, just a second. Can I contribute to
yes, yes.
answering to me?
Yeah.
So the intrinsic, not modified material has band gap, and it is not as good conductor. And the goal of KS work is to explore which modification of this material will increase conductivity. If you are fine with this answer, you can just stay muted. If you disagree, type something. Let's go to. Then Amir is typing to everyone, just polymer with continuing conjugated bonds in the backbone could be semiconductor. Yes, Amir, thank you. But it is not a question. Then Amir is asking, what is the polymer name again?
Polytectyline.
Is it just polyacetylene or some specific brand of it?
Sorry?
Is it just polyacetylene or you have more specifics about it?
I don't know more specific.
You do.
I do.
So is it cis or trans?
Oh, okay. I already said cis polytectyline. Cis polytectylines.
Okay. Yep. Good. And yeah, I think we are done with typed questions. So now please keep telling your story.
Okay. So like for the undot for every model, as I said that I did an anionic calculation and cation. So this one, I guess it's cation or anion. I need to check. It's yeah, neutral then cation. Okay. So this one for undot cation, and this one an undot anion. And from this, we already see that this occupied and unoccupied, it's almost like overlap with each other,
Mhm.
and uh, and we can see other figures as well that mm, and if we calculate the band gap from the data and also see the figure, then we can come to the conclusion that after doing the calculation, cationic calculation, um, this undocked cis polytetraline model will show more conductivity
Mhm.
than
Good.
other materials that
Okay. And if we are talking about panels B and C from the literature,
yes.
is there any specific name for when one injects an electron and looks how the charge in the polymer and modification of the nucleus are adjusting to follow this charge, are polarizing to follow this charge? Is there a name for quasi-particle?
Specific name?
Specific name for a state of conjugated polymer when it carries injected charge.
Uh, I, I forgot maybe. I didn't wrote here.
So please ask Aaron. Just
Uh,
ask him directly, and maybe he will be gentle enough to answer this question.
Hi,
Just ask
Aaron.
us directly, Aaron. What is it?
Hi, Aaron. What's the name of that material? Like when we injecting charge, then what's the name of the what's the scientific name of that? I don't know.
You might see the name Polaron.
Polarization?
Yeah, Polaron.
Polaron?
The polar is in like polar plus or minus charges, and then on as in particle.
Yeah, thank you, Aaron. So, okay, if you want to sell your results to professional community, you may tell like first principle calculation of polarons and conjugated polymers.
Okay.
Okay. Yeah, thank you, Aaron. So, more questions to this figure, or maybe Kay, you want to add something, or to this figure, or you want just keep telling about this figure, or go to the next as you find relevant.
I think this figure. Do I need to explain more? Because okay, I think. Okay.
I guess, do you see a connection between your
Mhm.
C and D panel, or any similarities?
C and D. Okay, so this one for different model. Doped in cis polytetraline, and we use P dopamine there, and this one neutral state, cationic, and then anionic. And this one for the co-dopped means cis polytetraline we add P-type and N-type dopamine, and again plot the same figure like neutral, anionic state and cationic state. And then actually we want to compare the result from that which model, like which state actually show more conductivity. That one. That's why I plot this figure.
Mm-hmm. And well, I guess the
Aaron, can I briefly intervene and just make your question more narrowed and specified? Maybe it's most favorable comparison between B and D, between removing electron from undoped and adding the oxidizing agent, the P doping. So removing electron by injection whole, or putting preparing the model with oxidizing agent with p doping. Is it kind of what you wanted to ask?
Yeah.
Okay. And did Kea answered what you wanted to hear, or not yet?
Maybe. I guess the thing that I'm just trying to get at is that, like, doping with these PF6s is similar to like adding or removing charges manually, or so they look
Removing. It's equivalent to removing electron.
because it's the PF6. That's a p dopant.
Yes. Okay. Amir, do you have a question about this aspect? Or comment? You should. Amir, are you? If you unmute microphone, we can discuss it briefly. You will enjoy it. Maybe he's busy. So in the work that Amir is doing, he and he was presenting it on this series of meetings. Amir was modeling the doping of polymers by injecting charges. But in his calculations, he, at least those he has presented in public, he didn't explicitly include P or N doping. And in some sense, the work of Kea complements the work of Amir, because Kea is proving that injection of charge and adding a dopant have equivalent influence on the electronic properties. Make sense? And if Amir is not protesting, it means he accepts it.
Yeah, I was also thinking about that. That could be interesting to have real dopants in the system and take a look to the results. And also, I have one question: why you didn't use, for instance, just a single dimer? You pack several dimer in the system. So, is there any specific reason for that? You increase the system size.
Let me try, and Kay will answer next question maybe. Amir, if the oligomers are stacked tightly, there is a chance of hybridization of electronic state between several oligomers, and this hybridization extends over several oligomers. It is interesting to have the model size larger than the Hoping distance of electron between chains. So if one includes only two chains, it will be too much of simplification. So it's more realistic if it is bigger. And for this quite simple polymer, it is just possible, because K selected the simplest possible conjugated polymer. Does it answer your curiosity?
Yeah, thank you.
Okay, yeah, thank you. And there is one more typed question from me. How does one determine more or less conductive when looking at this figure? Perfect question. Kay, would you please answer?
Can I see his question? Oh no.
I can read it once again from the chat line.
How
How does one determine more or less conductive when looking at this figure?
band gap, like
Yes,
if uh, if you
and
see that they are overlapping with each other, that means that figure, this state shows more conductivity. Means when we removing electron from the model, means the cationic state, uh, they show the more conductivity compared to the neutral state. Like this, there is a band gap, but there is not.
okay, and maybe Mead wants very some thumb rule. So if white and filled areas coincide, it is conductor. If white and filled areas are offset, it is more insulating. Okay. If there are no more questions to this figure, okay, please proceed as you planned.
Mhm. And actually, this one after MD is heating and molecular dynamic calculation.
Uh-huh.
So professor add those things here also. Um, so actually, after applying heat uh, and the molecular dynamic calculation, I want to see that is there any effect on the model or not? Is it reduce the band gap or not? So it shows that suppose, as an example, not exact number, like suppose it was for the undoped neutral state, like it's band gap zero 0.3, then after heating and molecular dynamic calculation, its band gap reduced almost, um, I forgot the exact number, but it reduced a lot.
Okay. Yeah.
That's why I got this one.
Uh-huh. Okay, thank you. There is a thermal excitation of electrons. Okay.
And the result also showed in the paper, means the difference between the normal state, means neutral, and after heating. What
Okay.
happened in the band gap?
So if there are no more questions for this one, let's keep going to stay in time.
So this one actually we explained before, like band gap, those kind of things.
Okay.
And these things actually change. That's why I this actually they after doing the after plotting the density of state and form that figure, we able to get we able to know the band gap, and after that we are plotting absorption state absorption graph. So like we I showed here this one and the table, and from the table we can see that uh, this one actually um, uh, band gap less than others. So if we plot the absorption spectrum in a transition with transition energy, then it shows that the undoped model in a cationic state, the absorption spectrum is too much higher than others. Means it's like reverse. Like if band gap low, then absorption spectrum will be higher than others. Yeah.
Okay. So this figure is
And
open for
yes,
discussion or
higher
for
higher absorption means high in that material will show high conductivity. That's
So
so.
this figure may induce a lot of questions.
Yeah.
Let's check if anyone wants to ask. Aaron, do you have questions to this figure? It is okay to protest against it and even argue with legitimacy of this figure. Kay and myself are ready to defend.
I guess on the right hand side, so conductivity. And what's W? Is that like frequency?
Mm-hmm. Oh, I shouldn't answer. Kay, please take care of my answers.
Sorry, can you say again?
So in the top right corner,
Yes.
and if you go up, so you have ABS W equals 0. So is W. So what does W represent?
So Aaron is not criticizing your results yet. He's
Okay.
just asking for definitions.
Yeah. So it's W. Is that like the frequency?
Yes, it's a frequency.
So is that like a general definition of conductivity as frequency, as the transition frequency goes to 0? I guess I'm asking, I don't know.
Yeah, Kay, please answer to your best understanding.
Like when transition energy, it's I can say like this way, like when transition energy at 0 point, it show all model actually show their higher values. So I just want to show the result of the 0 state. When transition energy is 0, I just want to show the value of the all model of the absorptions. When transition energy is 0, absorption spectrum of the undoped cation is 2.3 something like this.
Okay, so Kay, you are giving practical examples, and Aaron is asking about principles. Let me try to convince him.
Yeah.
So the current means that there is non-zero momentum of a charge carrier, and voltage means one applies acceleration to a charge carrier. And in some sense, one needs to assess how easily a carrier will pick up velocity if there is a force applied to it, or if there is certain energy applied towards charge carrier. No criticism yet.
Not yet, no.
Okay, now it can be reformulated. Would the charge carrier accept energy? Would it allow excitations if one tries to apply infinitesimal amount of external energy? If there is external quantum of 0 frequency, would it make any change to the charge carrier? So if the system is wide gap insulator, then it will not accept any energy, anything with infinitesimal energy. If it is a metal, then even small frequency excitation will give energy to a charge carrier and make it move somewhere. and this is alternative definition of conductivity based on Kubo-Greenwood equation, if we need to set up detailed justification.
Okay, so it's just another way to define, I guess, resistance. I guess conductivity and resistance are
inversely proportional.
Okay.
So you do not need to sign your agreement in blood. It's quite natural to resist and argue if something is unusual. But and there are more questions from me. We'll answer his questions. Yvonne, if you are not busy with other things, would you be interested to add to the discussion of this definition? Just share your vision, your impression about connection between conductivity and absorption, or your skepsis to this, or your enthusiasm, just general discussion about this connection or lack of connection between these two concepts.
I guess so far everything is good. Because previously we used this kind of scheme, calculate the photoconductivity for power spec and for, I guess, for other systems. So approximately the conductivity is proportional to the absorbance at the 0 wavelength.
Okay, so correct or not, but reviewers accepted it, and papers are getting published. Okay. Yeah, thank you. So there are two questions from me. First one, what is absorption spectrum analysis telling us? Okay, can you summarize the answer?
Most of the questions are higher level questions.
What is absorption spectrum analysis telling us?
So from my understanding, from the absorption spectrum, we are able to see the energy.
If the molecule accepts energy at certain transition energies, if electrons can be promoted to the higher states, if the resonance conditions are matching. So in some sense, absorption spectrum tells about resonant conditions. And in this specific example, it tells if there are some resonant transitions with 0 frequency, which is available only in metals. So next question from me, do the shapes of the lines tell us anything?
Which one?
Do the shapes of the lines tell us anything?
Shape of the line.
Maybe you can go to the next figure and then address this question.
Yeah. So it's absorbance.
Yep.
Graph wavelength. So what we are able to see that the undoped cation.
No, your mouse is moving not in the right place. You should move near 3000 nanometers. Yes.
Okay. There is a highest peak. That's why I showed here.
Okay.
Okay. So in the app, what we just see in the absorption transition energy versus absorption graph. That at zero energy, transition energy, there is a large amount of absorption. It shows large amount of absorption. But in the in this graph, it's like in a reverse way. Like at zero, it shows the lowest value, but when the wavelength increased, like here we are able to see that around 3000.
So you wanted to say that zero transition energy would correspond to infinite infinite value of the wavelengths, infinite wavelengths, right?
Yes, it's okay. Your sentence is good. My one is like okay. So it's like that yeah, when wavelength increase, absorption spectrum will be increased. But when wavelength is zero, then it will be show zero, not zero, it's less absorption spectrum.
So, Mead, the goal of this research is not interaction with light; it's more assessing the value, the conductivity, which needs only the value of absorption at zero frequency. So shapes of lines is not as important here. So more questions to these figures, this and previous one? No. Okay, Kay, please go forward as you find reasonable.
Why it's not moving? Oh, Professor, just one.
Yeah, it's fine. It's fine. And
connect my.
Yeah. Please go ahead with recharging, reloading. And if something will happen, I'll just share your slides from.
Yeah.
Do not worry.
Let's see.
So while Kia is reestablishing connection, let me give a intermediate introduction what we expect in the remaining part of her work. So in some sense, she has presented the main result, but now there will be a very large amount of figures with orbitals, which are quite challenging to interpret. And the main thing to bring her results to discussion is to analyze those figures.
Okay, so it's better if we see from the slide, not from that. Yep. Okay.
And maybe go into presentation mode so that it will pump up to the whole screen.
I don't know, it's not working. It's working.
Yes.
Yeah, it's working. So presentation is not ready yet. It's just plotting.
So just explain to your best.
I think Professor, you need to share the screen.
Okay, you do.
Because
do not worry. Do not worry.
I think internet connection is not.
Yeah. Kid, do not worry. We'll do it in a second.
I don't know. No. Yes. What should I do? Connection to the remote was lost.
That's okay. You can stop sharing.
Yeah.
And maybe email me the slides. Because in this in the figure the resolution is not
It's not good. Yes. Um, no, connection is lost from my side.
Okay, yeah, I'm sharing. So please try to explain based on this figure.
Okay.
And explain only the first one in all details before going to anything else. Just give details what is here in the center.
Just 1 minute.
Mhm.
So here we are able to see the charge density graph for that one, the 5A. It's for the HOMO -1, and this one for the cis polyethylene undocked model. Means there is no dopamine or nothing included there. And the blue one that we are able to see with the like a cloud is 3D isosurface. Mm, and there is in the uh, I'm not able to see, it's jade, yes, in the left side. um, that one actually shows the projection on the z-axis, and the below that figure it shows the projection on x-axis. Yes, x-axis. uh,
So now please explain what one can learn from each of these projections.
okay. From that projection, we are able to see it's like suppose this one x in position x, there is a peak like this one, highest peak. Yes, the highest peak there is large amount of charge density. So and in the middle position in the in the x direction in the there is, yes, in this one in the middle it shows the higher density rather and if we go to the edge it shows the lowest charge density. Similarly, these things happened with the uh, z axis.
Wait. Please explain more about this X dependence.
Okay. So
why is there are individual peaks? Why is the line is not continuous but it is composed of several peaks?
okay, so this peak actually because of this like cloud this uh, orbital. It's like there is cloud type shape. This one. So here maximum. That's why it's peaking high. And like in the edge, if we see from left side from yes from desktop left side, there is see only in 1 and 2 5.
No. Okay, please keep explaining this X dependence.
Okay.
Tell more about particle in the box if you remember about it.
Okay. So like at the edge there is only in one, two or type cloud. It's not clouds. What should I say? It's not cloud. It's charge density. No. What's the charge density, or is there any
isosurface?
Isosurface. Okay. So at the edge there is only we are able to see that in the third oligomer there is one, and in the last it's there is one. That's total two. So in the X projection, that's why it shows only in like 500, sorry, 5,000 charge density. But if we go to the middle section, from 15 to 20 in position, it shows maximum density around mm, 35,000.
And why there is a peak in the middle and why it goes down as you go to the edges?
Because of the because of this the shape of the orbital means isosurface.
Let me give a hint.
Yes.
So, if anyone asks you this question, tell because of particle in the box. Electron is a particle, and this simulation cell is the box, or the oligomer is the box.
Okay.
Okay, let's check if before you explain the panel A, let's check if anyone wants to ask questions about the interpretation for this dependence along x-axis. Aaron, do you have question or maybe comment or your own version of the interpretation?
I guess to me it looks like my expectation before doing the calculation, I would expect the blue clouds to be everywhere and kind of even distributed. So in your 5A panel, it's obviously like some spots there's more than others, but if you combined like your 5A and 5B orbital panels, then it would look more as how I would expect initially. Because those are HOMO -1 and HOMO, right?
Yeah.
Yep.
This one 5A HOMO -1.
Yeah, so you can see it's like for your HOMO -1 where there's the most density, that's where it's kind of lacking in your HOMO. But then where there's a lot in your HOMO orbital, that's kind of where it's lacking in HOMO -1. So that's how I see it from looking at it for a couple seconds.
So what you're telling is that if we would look over all occupied orbitals and add together, then the charge density will be equally distributed over all carbon atoms.
More or less.
Okay. And
the orbital I don't like anyway.
Okay. And do you see anything similar to progression of ground state for a particle in the box? Looking on the individual oligomer as a box, as the edges which have non-conducting ligands like ethane groups with C2H5. So there are terminations, and then the charge density is enforced to be in the center of a strand.
Yes.
So can you comment about it with your own words? Like, what would you expect if one would take only one oligomer in the simulation cell? How would progression of like HOMO plus 1, HOMO plus 3, or HOMO -1, HOMO -2, how this progression of orbitals should look like?
So I guess if you were just trying to do it by pen and paper, you'd expect like I can't think of the words. Nodes. There we go. Standing waves. There we go.
Okay.
Yeah. Yeah. So similar to particle in the box. For just a single strand.
Yeah, single strand, single oligomer. Okay. Yeah, thank you. Anyone has more comments or questions to this dependence on X variable? If no one has, then here, please go forward with explaining projection on Z axis for this panel.
Okay. So for the projection of the position of the z-axis, we are able to see that there is, oh my goodness, not able to. There is a highest peak around position 5 or 6. I can't see. Okay, this one. So the arrow professor showed, there it shows the highest peak because of the oligomer, like this way. There is the maximum amount of the charge density shows there. That's why there is a highest peak on that section. 5 to 6, I guess. And then then the second peak we are able to see the next position. We have the pink arrows. It shows in the second position there is the there also we are able to see that there is some charge density in the second oligomer, and I think there is some what like there is some vacancy inside there. So there is it's like in the first oligomer there is no empty space, but in the second oligomer, see we are able to see the empty space. It's like a hole inside there. So I think that's why it affects the charge density, and that's why there is less amount of that violet this one. But
okay,
we see the third oligomer, that one showed the highest amount of charge density.
Okay, yeah, thank you. How do you interpret the fact that space between these two arrows gives non-zero integrated charge density? Why in the space between oligomers there is you see this blue clouds right in between strands, right in between oligomers?
Yes.
Can you explain, or just focus our attention on the fact that there is a non-zero orbital amplitude in the space between two oligomers?
Like from the isosurface, it's not. But from the position of the Z, it seems like that their difference is not too much.
Okay, so they are compressed so close so that orbital contributions from one oligomer and another one overlap and hybridize. Okay. Let's check if there are questions to this feature that you have computed. Amir, do you have any questions or suggestions or criticism or any comments?
I'm good. No, I do not have a question or suggestion right now.
Okay. Do you expect similar effects in your systems?
Yeah, so it's a little difficult for me to completely compare those systems, because for my system that was just some single chain in the periodic model. But
right, yeah. Right. But you are working on compressing, on making the realistic density system with at least two oligomers with interfacing each other, right?
Yes.
And the buckyball that will be touching this strand. So this stacking on and overlap of different molecules, different oligomers, is expected to be observed in your work as well.
For sure, yeah, in that system, yes.
Okay. Aaron, do you have? Yes,
I have another. It's not a question. It's my understanding. Like the portion there is nothing, that clouded part. Like it's not showing the charge density. That can we use the delocalized term? Like it's not delocalized. That's it. Localized, delocalized.
So localized means it is in a very, very local, in near specific point, and delocalized, it means spread everywhere. Aaron, do you have interpretation or comments to this observed trends?
Are all the oligomers the same length? Like some of them have to be shorter than the other, right?
Yes, there are 4 longer ones and 2 shorter ones to keep a bit space for the future introduction of the dopants.
Mm-hmm.
So it is a little setup, but in realistic system, there could be a distribution of oligomers of any length.
Right. And then the ones closest, well, I guess which ones should be closer to the conduction and valence bands? I guess the shorter oligomers will have a wider band gap.
Mm-hmm.
We'd expect their orbitals to be further away from the overall band gap.
Yes, especially if they will be spatially isolated in space. But since they are compressed close to each other, the overlap of orbitals belonging to different oligomers starts playing dominant role.
Mm-hmm.
So personally, for me, these results of KEA were very surprising. I was expecting each eigenstate, each orbital to be localized only on one strand. And here, like adiabatic states on one strand. And here it shows some mixture between several strands. It will give non-zero conductivity in transverse direction, not only along the conjugation length, which is, for me, it is unusual.
Yeah, it could be an artifact of PBE.
Oh, so you think if one will redo orbitals with HSC, this effect may disappear?
Yeah, if someone wanted to be thorough, it would be something to check.
Okay, so your expectation is that the projection on x-axis will stay the same, but projection on z-axis will include only single peak if one will do everything in HSC.
Ideally, yeah.
Okay. Yeah, thank you. Thank you. It's an interesting and valuable suggestion. Maybe not possible to realize before exam on Friday for Kia, but if she decides to pursue it, not exam, presentation, do not fear this word. But if she decides to pursue it further, it's, yeah, good suggestion.
So it's not correct? I didn't get it. What
okay, ask Aaron for his opinion.
Aaron, you just said that you are expecting from this HOMO -1 charge density graph that x-axis all will be the same. It's not like this. Why?
So it's not wrong because it's what's, well, I guess it's what the software like computed. So in that respect, it's not wrong. But there's a known general like trend. I don't know how much you've talked about functionals in class, but like the common one, it sometimes results in the orbitals being too spread out. They become too delocalized, which is a known thing in the community. And then a way to correct the orbitals is to use a higher precision method, which is this HSE06. So if the orbitals being too spread out is an artifact, using the HSE06 would be able to determine that or not.
So what Aaron is suggesting is that if HSE06 result would duplicate, will reproduce the same result, it will be more available and trustable. So when needs.
So it's just more of an issue of like the software.
Mm-hmm. Okay. Are there more questions to this specific slide or trend? So everyone is welcome to either speak or type. And if no, Kia, please continue the story or bring us to conclusions, whatever you find reasonable. And tell me if I need to move to some other slides.
Yeah, 5B.
Oh, just this one. Okay. And we need to be done in about 20 minutes.
Okay. So if you did all this, yeah. Okay, so from 5B, it's HOMO orbital. This is like before plotting this graph, what I expected that HOMO orbital will be show more charge density. It will show more charge density, but here we are able to see that this one shows less charge density compared to the HOMO minus 1. And in the X position, from the isosurface, we are able to see at the edge of the both sides, and there is a highest peak like this. Like at 0, not 0 or 1, in the X position, and there's charge density more than 25,000. It's around 30,000. And at the edge also there is a peak. It's the highest peak. So it's and in the middle position, their charge density almost it's not 0 or less than the edge.
Okay. Are there questions from Amir or maybe a comment? I remember that Amir may tell something about states, orbitals that show continuous delocalization and some connection to mobility of the charge along this axis. Amir, would you please comment? Like, is it favorable or disfavorable for conductivity if the charge density for a certain orbital is delocalized over the whole simulation cell?
So for sure, when we have delocalized orbitals, they provide some kind of uniform distribution of the charge actually distribution through the backbone. Mm-hmm. So it would be easier for charge carrier to move through the backbone mm-hmm. and actually conduct the charge and current. So it should be ideal for the system to be delocalized through the backbone.
Okay. Yeah. Thank you, Amir. Everyone is welcome to type or ask questions. Kia, where should we go further?
Yes. And in the like in the Z position, we are able to see the highest peak. It's almost in the middle position. In the middle position, it shows the highest amount of charge density. But in the LUMO, it's LUMO, there is charge density only, it shows only the third oligomer. The third oligomer shows maximum charge density. And in the X and Z direction, both like the third oligomer, that one actually shows the maximum charge density.
Okay. Can we go to the next?
Okay. And 5D, it's LUMO plus one. LUMO plus one orbiter. And here we are able to see that it's a similar like LUMO. Like in the LUMO, we see that the charge density, highest charge density, we are able to see at the edge of the box, like in the X position. Similarly, in the LUMO plus one, we are able to see the maximum charge density at the edge of the box X position.
Okay.
Yes. And so, I plot charge density and for all models actually. So this one for undoped, doped, and co-doped.
Okay. Let's go forward.
Rest of the model is same.
Yeah, it is a little lesser resolution. So
do I need
to we should about to finish soon, but do you have any general observation for this p-doped model?
In the p-doped model,
so let me share my observation. So the charge density seems to select the space between these two dopants, and it is reflected both in X projection and this Z projection. And the same trend is seen kind of in other images. The trend looks opposite here, but also since it is periodic boundary conditions, these two orbitals, they are also stacked to each other, and they, to some sense, are connected to each other through stacking. So differently from the undoped model, the charge density prefers the space between the dopants. So presence of the dopants themselves do not carry charge, but they affect charge distribution on the nearby strands. And this is very similar to the project that Dr. Khan is doing. He was not showing orbitals today, but in his project also this covalent doping doesn't have any charge on itself, but it affects charge distribution on the conjugated system nearby. So
this one co-dopt, and obviously this here we add p dopamine and n dopamine, positive and negative charge, and it shows that like this one, it's this. Can you? I don't know how to. This one, like in the second oligomer, we are able to see dopamine, the pink one, and for that dopamine actually it's affect the charge density, That's why in that oligomer there is nothing, almost nothing. And after that, it shows the charge density in the third, fourth oligomer. So that means that if we use dopamine in the polymer, conjugated polymer, it affects the charge density and also affects the conductivity.
Yes. Okay. And is it the last figure?
Yeah. Yes.
Oh, this is too technical. I think this can be skipped from the story. This you already showed before.
Yeah, actually, this may. Okay, I already sent you the latest version. It's not the latest.
So when you will be presenting on Friday, you need to squeeze everything you presented today in hour and a half into 5 minutes.
Yeah,
and add movies of molecular dynamics.
Yes, and I think today's session will help me to present.
Yep, yeah, we are recording. We'll share it. Would you like to briefly summarize before we dismiss the meeting?
Okay. So what we are able to see from this the whole project conclusions, the whole project, and that like if we injecting charge, and we did two things. One, injecting charge, another one is adding dopamine. Okay. So from that we are trying to explain that which one will be show more conductivity after injecting charge or adding dopamine. Yes. So after that all doing all the calculation, we are able to say that when we injecting charge, removing charge from the model, it will be show more conductivity. Means that polymer will be behave like metal. It's their behavior will be changed. They will be behave like a metal, and I think what we are doing this kind of things because in the industrial field we are looking for the material which will be which we need uh, like in the electric field on other field we need a material which is produce more conductivity. That's why.
Okay, so I invite everyone to join me in thanking Kia for interesting presentation.